let's begin. Before we begin, it seems like there's a lot of questions about something. Any questions? Yeah.
Where the covariance matrix?
Yeah.
How can we kill that?
Okay, so good question. You've got this MCMC you're doing, and the whole name of the game in MCMC, it always looks like this. Getting your code running, the trace plots forming is like the first 2 hours. And then you go and fix it. You go and you fix it, and you go and you fix it. This one's pretty straightforward because it's at least Gibbs sampling. And so as long as you have your distributions encoded correctly, it shouldn't be a lot of like, what's wrong with this thing? Do I need a new proposal? There's no proposals. The full conditional is the proposal. So, so you got all these parameters, and we asked, how do you check to see if a matrix is converged? Anybody want to answer that question in its full-blown glory? It's what I've already said. What's that? So, Lena says determinant.
Actually, I have a proposal. Is it eigenvalues or?
Eigenvalues. So I don't know that these are answers. Determinant.
The norm,
you know, of some norm or something like that. So you monitor the determinant and you show the trace plot for the determinant is what Lena said. Yui says, let's look at all the eigenvalues. Maybe that's something as well. You can also look at the eigenvectors. So you can look at everything. So the real answer is you look at every entry of the matrix and you monitor that for convergence, but you can imagine how overwhelming that is if you have a bit matrix. And so Lena has a good suggestion. Look at maybe features of the covariance matrix. So, well, let's start with the eigenvalue one. So how many eigenvalues will there be in a 2x2? It depends, but if the thing is not rate deficient, then there's going to be 2 of them that you can monitor. And that's a proxy for monitoring features of the covariance. Lena said to look at the determinant. So she's saying look at the product of those 2 eigenvalues and look to see that that thing's converged. And so if the matrix is converged, the eigenvalues should converge. All the features of the matrix should converge. You can look at the trace, the sum. So you're kind of looking at 2 different geometries. One is kind of an ellipse, and one is a square, or a rectangle. The trace, to me, is a rectangle geometrically, and the determinant is an ellipse. So I'll let you think about that. The reality is you monitor anything that you think is going to be useful. And so I like to monitor one thing more than anything else. If I'm going to monitor one-dimensional thing, let's say I have a space with 1,000 parameters, and I am feeling super lazy, and I just want to check one thing. What would you check?
The maximum value.
Can you say it again?
The maximum value.
The max. So that one's going to be a little bit hard because you're going to be getting all these samples out of things. So which maximum? Max of what? You're in a high D space. So what's the max?
I was thinking it would be the max elements in the matrix.
Okay, the maximal element in the matrix. So that's one thing. I would probably rather have the eigenvalues because it takes into account more things. So that's an idea. But I'm talking about a 1,000-dimensional arbitrary parameter space. Let's say you're trying to monitor that. What would you monitor if you're going to draw a trace plot? I probably wouldn't make 1,000 trace plots. Of what? Of all those parameters? That was my first thought. What if they're like covariance elements and mean vectors and variances, and the mean wouldn't mean very much to you. You're not going to report it. I don't know why you'd average all those things. So probably not something I want to report, but I guess if the whole thing has converged, then the mean of whatever is going to converge. How about the thing you care most about? The model. So I can plug all those parameters back into the likelihood function and make sure that thing is converged. I can plug it in and multiply by the priors too, so I can see if the likelihood function is converged or the posterior is converged. That's one-dimensional. So I always monitor the likelihood function. And then I usually do something like I monitor the determinant, the trace, and then maybe some of the other parameters as well. But yeah, you take various norms and you check to see that they won't converge. Now, it's possible that you could have all those things converge, but weird stuff happens and the parameters themselves haven't converged. So I'd probably monitor some of the parameters as well. But chances are, if the likelihood is converged to something and some other features, some other norms that make sense, things that you're going to report, if converged, I guess all is good. My real answer is anything I'm going to report, I monitor its convergence. And so I make sure that that's converged. So there's no, and this is true for optimization, for anything, any iterative algorithm, is you can't know for sure that you've converged to the truth. So unless you knew a lot about the distribution, symmetry properties, so you'd have to do some sort of analysis of the distribution that you're looking at. So maybe if I knew something was normal, then all I need to do is monitor the mean and the variance. So that's what I mean. So still no guarantee, though. So we want all the area in every little portion of everything to converge. So oftentimes what I'll do is I'll make intervals, and I'll check to make sure my intervals cover the truth. So what I always do, this is a little bit more advanced, is I build a model first. I build that whole rat sampling model. In our context, it's the rat model. So I'll build that model and I'll simulate data out of it. So how do I do that? You follow the iterative process. So I generate some, I'll have some theta naught for my random effect distribution. I'll generate that from some probability distribution. I'll use a conjugate prior usually to do it. I usually use that prior to use as my, I'll use that generating distribution as my prior. Then what I do is I build 95% HPDs for all of my parameters, and I usually change the parameters. I do this over and over and over again. But I generate some parameters from random. I use whatever the randomness distributions are as my priors. Then I generate data, new data set. Then I take that data and I run my Gibbs sampler on it. And then I make sure that whatever my truth was that I generated from, I'm converging close to that. So here's something you can remember. If I generate my parameters at random, so of course you don't want to just use the same parameters every single time when you generate data, but if I generate them at random and I use those as priors, my HPDs, my 95% HPDs, should cover the true parameter 95% of the time. So I'm going to use this frequentist thing to validate my Bayesian code. And I'm going to check to see if my intervals are covering 95% of the time. That's what I really do, and I make my students do it when they make me Gibbs samplers. And if they...
Welcome back, everybody. At the end of class, I had noticed that my camera had cut out. Hopefully that doesn't happen again. So I'm just back to recap what I had said this morning during lecture. Just a quick point. Homework will be due on the Monday after Thanksgiving. We spent a little bit of the morning talking about convergence diagnostics in MCMC, and it seemed that people needed a little bit more time making sure their MCMCs are running correctly. So take that time and try to be judicious with it and return it to me on the Monday following Thanksgiving. If you have gotten everything to work, kudos to you, that's great. Just as a quick recap, what I said to do is monitoring convergence means monitoring anything that you're willing to report. Ideally, in a large covariance situation, you would monitor every element of the covariance and make sure that it's converged. But in a very large covariance setting, that would be virtually impossible. So if you had maybe, even if you had like something like 1,000 by 1,000, so 1,000,000 terms in your covariance, you're not going to be able to monitor all of those. And so what you might do is you might look at the trace or the determinant or any feature that you want to report to somebody. I always recommend monitoring the likelihood function, so taking all of your parameters at each iteration, plugging them back into the likelihood function and looking at that trace plot. I'll be giving you more MCMC problems throughout the semester, so try to be judicious about getting your MCMCs working, because if you have bugs in your code and you're reporting things, even if your modeling methodology is really great, if your computation isn't working, you're going to be reporting something wrong, and that's not what we want to do. Okay, so homework is going to be delayed on the turn-in. And for the rest of the lecture, I spent some time talking about the interval hypothesis test. And I put a paper out online. So paper was called What P-Values Are and What They Are Not. Okay, basically what Shervish is going to spend his time talking about is that p-values are not measures of the hypothesis. In this paper that Shervish wrote back in 1996, illustrates this quite nicely through the interval test. So I'm going to say a few things about the interval test, and then I'm going to refer you back to the paper that I posted online. I'll tell you what the p-value is. We looked at the paper in class, and if you're here for that, that's great, but you can look at it online. And I'll tell you everything that I said about the paper. So let me just tell you what the test is. So here's the basic example. So our example is just, we have one data point. It comes from a normal model with known variance. So this is going to be known. And for this paper setting, they're going to pick it to be 1. So sigma squared is 1. If you did see more observations, instead of just using x to try to test what mu is, you would probably use x bar, which is the sufficient statistic, and then your variance would get scaled to n. So instead of using sigma squared over n, in our case n is 1, so that's going to be 1 over 1, which is just 1. It would turn into sigma squared over n, and if sigma squared was known, it would be 1 over n. I'll say a little bit more about that as I write down the p-value for the interval hypothesis. So here is the hypothesis that Shervish wants to test. H naught. Mu is an element of this set. Mu1 and mu2. And the alternative is the complement of this. Mu is not an element of mu1 and mu2. Now I would say, I really wish people would do this test and spend a lot of time thinking about what is mu1 and mu2 in their application. I.e., how far can you be out to the left or to the right before you're willing to reject something. And so this kind of has an auto effect size built into it, since you're testing on an interval. So I think that's a really good idea. I'm not going to say more about that without context of a problem, and I wouldn't know exactly how to pick these if you just gave me this general problem. I'd probably ask you lots about what is that measurement and how precise are you in making that measurement in the first place. The p-value for testing this is this. So here's our p-value. I'll make sure that I get this in the right direction. And I'll try to explain what this is. So this is going to be the normal CDF. And it's going to be added to another normal CDF, x minus mu2. And this is going to have some condition. This is if mu1 plus mu2 divided by 2 is going to be greater than x. They have it written a little bit differently in the paper, but that works for us. Or else, it's going to look like this. Mu1 minus x plus cat phi mu2 minus x. So the only thing that's different in here is a negative flip on here, where they're just flipping around the arguments. So this will happen if the average of mu1 in mu2 is going to be less than or equal to x. I can put the equal sign anywhere. So this is a continuous problem, so that never happens anyway. And so arbitrarily, we can assign the equal sign. I want to just show you what this is actually testing. And so what this is a measure of. And so this is really a measure of how close x is to your endpoints. So I have some interval right here. I've got a mu1 and a mu2. And I've got some x, and basically this is just measuring how close you are to mu1 right here. So the average is right here. So I'll call that mu bar. So this thing right here is mu bar, the average mu. And so it's really just asking you to flip the argument around if x is on the right-hand side or the left-hand side of this. So if x is less than this average, right here, then we would end up using this form. I need to make sure my directions are right. And we can check that. And so if you ended up using the wrong one, you'd get p-values that are potentially greater than 1, and we can't have that. I want to say a few things about how this is derived. So the idea here is that they're going to use the likelihood ratio test statistic. They're going to form that max likelihood ratio test statistic, and they're going to threshold it. For a non-Bayesian, this is a little bit of a difficult question because it's a question of which mu's do you plug in. And the uniformly most powerful test for testing this hypothesis right here comes up with a p-value that has this form. This is equivalent to thresholding the likelihood ratio test statistic. This is not a p-value that is well described in different statistics classes because there's numerous problems with it. And what we're going to see in a moment is the p-value itself is not a measure of the hypothesis, but rather if p ducks alpha, alpha is control on the type 1 error rate, and you have a uniformly most powerful test. That is, if the alternative is correct, then what you want to do is you want to reject your test. But if you fail to reject your test, i.e. you accepted the null, and I don't care if you use that language, or if you fail to reject the null, same thing in my mind, at least in terms of a decision, then you're going to be making a different type of error. So if you fail to reject when the alternative is true, you've made a type 2 error. And so by thresholding the likelihood ratio test statistic, that ends up minimizing that error, which is equivalent to maximizing power of your test. And this is the test that does that. So the paper that's online describes that to you. This was derived by Eric Lehman a long time ago. There's no relationship to me. He spells his name differently as well. But you can read through that. So again, what this is these are just normal CDFs. So this is the normal CDF. Is I'm adding value from negative infinity. I should probably do it on this side. Negative infinity over. So it's the left tail probability. And we're just adding those together. One thing I'd like to point out is that the interval test in its limit also consumes the one-sided test and the point null hypothesis. So as mu1 goes to mu2, i.e. they're equal to each other, this is the sharp test. And for the one-sided test, so that might be something like where I have mu1 is going to be going to negative infinity. Or mu2 is going to go out to infinity. So these are the one-sided tests. So let me just show you something. And this will already describe to you that the p-value is not a measure of the null hypothesis. Rather, it is part of a procedure for controlling error rates. And that's what the Neyman-Pearsonians do. And so if we just look at this, if we are doing a one-sided test, if a one-sided test gives your p-value, and I'll just call this p. So that's the actual value, so i.e. maybe that's 0.04 or something like that. So what that is let's just say I was doing a one-sided test where mu1 was going off to negative infinity right out here. This CDF right here would go to 0, and I would just be left with this CDF, and that would contribute my p-value of p. However, if I were doing the two-sided test, i.e. the sharp test, and that's what I usually like to call it, the two-sided test, its p-value would be equal to, and if I look at this formula, let's say we're looking at this case where this is greater than that, then this p-value right here, mu1 and mu2 would be exactly the same values right there. And so I'd be adding this thing twice, and this would be 2p. We discussed that pretty quickly this morning. And we already knew this. So if we go to a Stat 101 class, and they have you computing p-values for the one-sided test, at least in this example, if you computed p for your p-value in the one-sided test, the two-sided test would give you a p-value because you'd be adding together both those tail probabilities would give you 2p. And we can see this. And so the one-sided test and the two-sided test are in here, just in terms of limits. And so this is the only test that's left. I want to point out that for a hypothesis that's one-sided, i.e. let's say we're testing something like this, is mu naught over here. So is mu greater than mu naught? We'd be testing everything over in this interval right here. And for the two-sided test, you're just checking the endpoint of that interval. So if the p-value was a measure of the null hypothesis, then if I made this set bigger and bigger and bigger, it should be measuring something that's greater. And so if we think about, if we were just going to test mu in the entire real number line, does it live between negative infinity and infinity? What we should discover is that there's great support for that. Your p-value should come out to be 1. Anybody that's being rational should say, yes, mu is in the real number line. So as the set gets infinitely large, then the measure, if whatever you're using to measure that hypothesis, should climb to 1. And that's not necessarily the case for this p-value when you do the interval test. I will say that if you took this out to negative infinity, sorry, this out to negative infinity and this out to infinity, this thing would go down to 0, and this one would climb to 1 right here. And the reverse would happen here. This one would be 1 and that one would go to 0 if we were in this case right here. And so this does limit to the right thing. But I want to show you more specific values here. And so right here from this alone, you can tell that the p-value is not a measure of the truthfulness of that set. Right here, this right here, what I'm testing just at an endpoint, is this space right here for the sharp null test. This is going to be infinitely smaller than the size of this space right here. If that confuses you, let's run through an example and see this a little bit more clearly. So this is our p-value. And what Shervish is going to show us is that this p-value is not a measure of the null hypothesis, but rather if p-value ducks alpha, then alpha is your type 1 error rate. In this test right here will give you is the uniformly most powerful thing. So it has the greatest ability to reject the null if the alternative is incorrect. And if the alternative is true, then we're going to fail to accept the null with the highest probability, i.e. the error of making a type 2 error is going to be the smallest thing. So that's what this test does, and the paper will walk you through that. So let's just see an example. And this is what we discussed this morning. Let's say x was 2.18, and we'll see why Shervish came up with these numbers in just a moment. And we're going to test to see if mu is an element of minus 0.5 to 0.5. I coded this up on my computer so I knew what these actual numbers are. These are illustrated in the paper, but it's still good to see all this. So again, we want to test this. The alternative is the complement. And so let me just draw a picture. I've got minus 0.5. I've got 0.5. And I've got x is 2.18. So sorry, this isn't to scale. You just push that out a little bit more. I'll put it right here. And if somebody asked me that and they were looking at this, I'd probably say, well, the variance is 1. This thing looks like it's a couple standard errors almost out from here, so it seems unlikely. I'd probably be inclined to reject this, but I'd probably, in all reality, tell you to go collect a little bit more data if this happened. So let's see how this test performs. So what I'm going to do is I'm going to compute this right here. So this is going to be our p-value. I'll write it down here. Is going to be equal to psi minus 0.5 minus 2.18 plus the cumulative of 0.5 minus 2.18. And I'm going to compute that for us. Make sure I've got this number correct, but all I'm doing is I'm plugging this into norm CDF on my computer. So this is norm CDF. And I'm using that in MATLAB and just plugging that into the argument. Here we go. The number comes out. And I wind up for my p-value, and I'm just going to write it over here, just to keep track of things. My p-value for minus 0.5, when x is 2.18. So again, it's just this formula right here. This turns out to be 0.0502. And herein lies why Mark Shervish picked this number, 2.18, because he wanted this to be very close to 0.05 to be provocative. And we discussed what you should do with this. If you're following Neyman-Pearson's procedure, this is a fail to reject. If alpha was set to be 0.05. And And Fisher would like to argue about this and say, hey, that's really close to 0.05. We should be more considerate. But if you're just thinking about error rates itself, either it is or it isn't, Neyman and Pearson say you need to follow the procedure and fail to reject. So I ended up computing this for 2 more hypotheses. So let's consider those hypotheses real quickly. So I'm going to change this to 0.52. And I'm going to keep this one exactly the same at minus 0.5. So I'm going to consider this interval. And I want you to notice that this new interval right here completely subsumes this first interval that we had. And so it's slightly bigger. So we had a long dialogue about whether or not the p-value should climb or it should get smaller. And we had a little bit of debate. And at the end of the debate, most people agreed that this p-value should get larger. But at first glance, that doesn't make sense to you. Kind of think about what we first said, that if I took these and I blew them all the way out from infinity to negative infinity, what should the p-value be if you're acting coherently? It should be 1. And so it should get bigger as I make it bigger and bigger and bigger. And again, this interval completely consumes this. So if I budge the interval to the right and to the left, I think if the p-value was a measure of support of the null hypothesis, it should go up. We ended up doing this calculation. And this turned out to be, so minus 0.5 to 0.5, 2.18. Let me just make sure I've got my numbers correct. This went to 0.0521. So voila, that's good. The p-value went up, which at least matches some of our intuition. It should do that. Oh, this is a 5.2. So this is our second set. And then I did one more number right here. I entertained one more hypothesis. And I ended up budging this back a little bit to minus 0.82. I'll write it down here. And I kept this exactly the same, 0.52. So we did the same thing where we're just increasing the interval. And I increased this to the left-hand side, and I kept that to be the same. And so if the behavior is at least coherent, this sort of increasing should continue to happen. So unfortunately, it doesn't. So 2.18, and I'm going to go minus 0.82 to 0.52. Let me compute this and make sure that I've got the right number. This turns out to be 0.0498. So it got smaller. And this is what people are talking about when they say p-values are not coherent. They're not measures of the null hypothesis themselves. And although Fisher wanted that to be true, it's just not true. And this test really starts to highlight that. What a p-value does is if it ducks under alpha, it's control on your error rate, which is an entirely different thing. And so this demonstrates p-values are not coherent. And the reason they're not coherent is because they're not additive. That the p-value for the null, it's not the same thing as 1 minus the p-value for the alternative. They don't add up to 1. And the point null test already told us that. I want to just point out what a Bayesian does for this example. This should be compelling to you, that the p-value itself doesn't mean anything. And so rather, it's alpha that means something. A Bayesian does something entirely different. So what a Bayesian will do for testing the interval is they're just going to look at the posterior probability. So I'm going to compute my posterior. This will be pi mu given x. In our context, what is that? That's going to be a normal distribution centered at x, and it's going to have variance sigma squared. So, and that's if our prior is flat. I think I've already done a pretty good job of convincing us in a problem like this, because it's a shift parameter, probably a flat parameter. Flat prior is a good idea. This is also Jeffrey's prior. It's also the reference prior. That means it's transform invariant. It doesn't matter which scale you're operating on. So lots of good properties all the way around. And so this thing is going to be centered at x. And then I'm going to test my hypothesis. H naught is mu, an element of mu1 in mu2. And I guess to be consistent with our other example, this was like 2.18. And then I would have my stuff over here, mu1 and mu2. Those were all to the left. What a Bayesian does to test this is they're just going to add that mass together right here. So this is going to be an integral between mu1 and mu2 over my posterior distribution. And so for the interval test and the one-sided test, the Bayesian's job is pretty easy. The harder part is doing the point test. And I'm probably more compelled to do this sort of test right here. But I've said a lot about that already. And I'll let you guys do whatever it is you're accustomed to doing. But we want to just understand the issues. I want to point out that this thing right here is coherent, meaning that if I budge this to the right a little bit, it's going to increase the PDF, the density function, the posterior distribution is always positive, and so if I make that interval bigger, it's going to start collecting more mass. And I'm going to add up a little bit more mass right here. And I would add that in. And if I budge this to the left a little bit, then I would add in that mass. So if I ended up increasing the interval, so long as they all overlap the first interval, my mass will only increase, and that doesn't happen here. So this always leads to increasing mass if I increase the interval. So these all increase for these different examples. Mu is an element of minus 0.82. I'll say for the first example, minus 0.5 to 0.52. And mu is an element of minus 0.82 to 0.52. I haven't computed those for you, but you can compute those for yourself. But I think conceptually you can see that the area is increasing. And so the posterior support for the null hypothesis is going to increase. If I wanted to know the probability that mu was somewhere else, i.e. is it over here? Or is it over here to this other side? So that was my boundary. Then I would just take 1 minus my posterior probability for this hypothesis, and I would come up with the posterior probability that mu is in these other sets. And that's called additivity, because everything just adds up to 1, and that gives us coherency, and the posterior probability is a measure of the null hypothesis directly. Again, the p-value is just giving you a procedure to give you a number to see if it ducks alpha, and alpha is the important number when you're doing a Neyman-Pearsonian type hypothesis test. So it's error control. And that's about all I have to say about this. If you'd like to see a little bit more, just read through that paper and it'll walk you through this. I think that that's an important point. I did forecast a little bit about what we're going to do next in class. So let me take 2 minutes and tell you about that. So this is where we're going. I'm going to spend quite a few lectures on this problem and show you that there's a lot of different methods for answering these sorts of problems. So model selection. This is up next. And so I'm going to do this all in the normal framework for this class, but you could apply this to any sort of generalized linear model or any sort of linear effect that you're looking at. And it doesn't have to be normally distributed. You could change these error assumptions. Turns out everything's a bit optimistic in the normal case, so you usually don't have as good of model selection procedures when you change these error distributions. So this is our typical setup right here, where y is going to be a collection of values. These are our responses. X is going to be a collection of covariates. So this is going to be x11 out to x1p. This is going to go down to x n1 out to x np. This is all going to be filled in. Very typically, we let this column be a column of ones to represent the intercept. So we're going to multiply by some vector of betas right here. That looks like this is right here. So beta 1 down to beta p. Again, if you let this first column be ones, you would interpret this as your intercept of your model. And this is going to have some normal errors to it. Error 1 down to error n, where the error i's are normally distributed with mean 0 and variance sigma squared. And so the yi's are going to be normally distributed, and I'll write it out this way: xi transpose beta sigma squared. Or this xi transpose beta, what I mean by that is it's just this linear sum. So j is going to go from 1 to p. I'm going to have these covariates xi j times beta j. Right here. And so for this first one right here, it's going to be the dot product between that and that right here. And that's what's expressed right here. So that's our basic regression setup, our multiple regression thing, and it has a lot of interpretations that are easy for us. And so a very typical question is to try to answer, are these beta j's equal to 0? And depending on the procedure, you're going to come up with different answers to this question. This is a very commonly studied thing. And so I'd say it's entirely different if you're in a setting where you just go out there and you collect all the x's you can get your hand on and just see if they can explain the variability in y's. Versus if you scientifically went into something you know mechanistically should determine the variability of the y's, and you put all of those x's in it, and maybe it's a small subset of x's that you went in and you collected. In one case, you probably are going to want to induce a lot of zeros. And in the other case, you're probably going to want most of your stuff to be meaningful because you put it in there for a reason in the first place. So usually what we're arguing over is how hard we're penalizing whether or not the betas are 0 and how many of them are 0. And so what we're arguing about is basically how much we're regularizing the space. How much parsimony are we trying to get out of the space? And so there's a number of techniques that I'm going to give you. And we'll start with these first two ones, and then we'll move, once we get back from Thanksgiving, to point mass priors. So we're going to study three different procedures. So ridge regression. A lot of you are probably familiar with this already, but there's a Bayesian incarnation of it. We're going to study the lasso, and we're going to study point mass priors. Like we did in the case for hypothesis testing. This actually is my favorite thing to do, but it's the most computationally intensive thing to do. Ridge regression is tantamount to placing a normal prior on the betas. So this is going to be a normal distribution centered at 0, and there's going to be some variance. And this variance is going to help regularize the space. This, what I mean by this is going to be the 0 vector. right here. So we're placing a prior jointly on all of the betas. And I guess in that vein, I should probably multiply this by the identity matrix. So psi squared times the identity right here. This, of course, is going to determine how much regularization and how much we're going to push everything towards zero. So we need to discuss what that actually means and how you tune that. A lot of people have different incarnations that are not Bayesian and they yield the same solution. Tigranov regularization was something that was created way back in the 1800s, and it wasn't developed under a Bayesian lens, but there is a Bayesian way of thinking about it. We'll discuss that. This is going to be a double exponential prior. I'll show you what that is next time. And I'll refer you to a paper. And the point mass mixture priors are going to look like this, where I'm going to place a prior on each one of the betas. It has this basic setup. So this is going to be pi for beta j being equal to 0. So that's going to be my probability of that being true. I'm going to have a point mass on 0. And then I'm going to have an alternative variance. So this is going to be 1 minus pi beta j. And you might do something like this, where I'm going to center this at 0, and then I'm going to have some variance that's going to calibrate how far from 0 I need to be before I'm willing to reject it. I'm going to show you what's called the SSVS scheme. So it's an MCMC sampling scheme for not just doing the math, but working through this in an MCMC thing, because usually you need to figure out what all the betas are, maybe what your variance of your model is in the first place, what's the sigma squared pertaining to epsilon, and you're going to want the joint relationship between all the betas being in the model or not in the model. And so you usually need to do MCMC. This stands for stochastic search. Variable selection. And we'll get around to this after the break, and this will take a little bit of ability to code things up. So if you're not able to implement your Gibbs samplers so far, this is going to give you a very big headache. And so I encourage you to spend time making sure that your homework up until this point is complete, and that you've gotten through those exercises and you can get your Gibbs samplers to converge so that we can do all of this stuff. There's an analytical form for this problem, and this is another computational problem that will need some sort of an optimizer. You could maybe do MCMC here, but most people don't. So I'll see you next time, and we'll start picking up right here. So thanks a lot, you guys, and thanks for the patience on my flub video.